And we finally come full circle to our cardboard box problem once again. So this is a chance, if you didn't quite catch it in the previous sections, you could kind of try to see if you could remember the concepts or relate the concepts to help you out in this section. So let's start off again with the information that they're giving us. We're starting with a box, actually it'd be a rectangular piece of cardboard, so that's 2-dimension, and they're giving us the dimensions already. So we're starting off with a 20-inch by 40-inch rectangle. So I'm gonna include this in my diagram. Looks like the shorter side I have 20 inches and the longer side I have 40 inches. And we're cutting equal size squares from each corner and folding the sides up. So those equal size squares we have going on right here. And what they mean by this is we don't know the size of the square, so it's kind of hypothetical. So that's where we're going to use that X, and they told us to do that, so we will follow the directions. So basically you're cutting equal size squares all the way around. And if you prefer that you label the squares on each side, it sometimes helps us. So the idea is to try to understand what happens when we cut these squares out. What happens to be our new length and our new width? I'm relating that from 2-dimension now to 3-dimension on the right. So previous practice from this, we always started off with the length of the original cardboard, rectangular cardboard piece. And remember, you're subtracting off an X from each side. So that's subtracting off 2 X's. So that new length would be 40 minus 2X. Similarly, you're starting off with 20 and you're subtracting off 1 X from each side. So you're actually subtracting off 2 X's. So your new width would be 20 minus 2X. Also understanding, when you do fold up those sides, the length of the side of the square becomes the height. So you end up having a height of X. It's kind of an unknown variable. We're not sure yet. So now we have the dimensions of the box we're talking about so that we can start answering questions about it. First off being, again, you can't cut the square off to be too big, because if you cut it off too big, you won't end up having a box to make. So this is what they are talking about when they talk about the restriction. And so just as we did in maybe the previous sections, if we were looking at understanding the restrictions, we have to have the length must be positive, so it must be greater than 0. At the same time, the width must be greater than 0. And at the same time, you have to have a size square to cut off in the first place, so your height has to be also greater than 0. I mean, you probably already guessed this, but we just want to translate. Sometimes it's confusing in math speak as opposed to English. So you do have expressions for your length, width, and height now. You have 40 minus 2X, still greater than 0. At the same time, you have the width, 20 minus 2X, greater than 0. And then this time our height is an X. That is greater than 0. So we should have the and. Now, keeping in mind, these are all linear inequalities. So when we have the linear inequalities, what we would do is we'll solve for X. We can just isolate the X on one side, a little nicer. So we shall do that. If I solve this linear inequality for the length, I would get negative 2X is greater than negative 40. I always like to isolate my variable on the left side. Helps me with the direction of the inequality symbol. If I divide by negative 2 on both sides, the inequality symbol reverses. So I have x is less than, negative 40 over negative 2 gives us 20. And we'll do the same thing for the width. I'm going to subtract 20 on both sides, so that's negative 2x is greater than negative 20. If I divide by negative 2 on both sides, I have the inequality symbol reversed once again. And negative 20 divided by negative 2 is 10. And you know, sometimes you get fractions or decimals. Go with it. In real life, you get fractions and decimals. So let's look at that. I'm going to write that down one more time. That's x is less than 10. So now just to kind of keep everyone on the same line, we're looking at x being greater than 0. So we can kind of see that. Otherwise, we don't have dimensions. Now, if you really want to figure out, you know, what inequality or what restriction covers all of these all at once, this is where I would graph them all in a number line. And figure out where I've colored all 3 regions. So if I'm looking at this, plotting these in relation to each other, 0, 10, and 20, if I'm plotting x is less than 20, I'll do that in green. I have shading to the left, parenthesis opening up to the left. In purple, I have x is less than 10. So shading to the left of 10, opening up to the left. So I can already see where I've shaded twice. And finally, if I have x is greater than 0, I'm shading to the right of 0 and opening up to the right. So it may get a little messy, but I hope you can see that you've shaded in all 3 regions, all 3 colors are located in the region from 0 to 10. So your restriction, you can say that 0 is less than x is less than 10. Or if you want to write interval notation, you can say 0 to 10. But make sure you're dealing with all the numbers in between 0 and 10. It's not just 0 and 10, it's every single number that could work. So that would be the answer to part A. Also useful when you use your TI. So now we'll address item B. They want us to determine the volume of the box in terms of x. And technically, we already have the setup. We do have our length was 40 minus 2x. Our width was 20 minus 2x, and our height was x. So if we were going to talk about volume, we remember volume is length times width times height. So we can then include this, 40 minus 2x times 20 minus 2x times x. And sometimes you see, although it's not necessary, you end up seeing that they put the monomial factor first. It's totally up to you as long as you have the other factors included in parentheses. So we have our volume expression. And that's important to understand because the next 2 questions are going to be about volume. So let's look at this. Item C, find the value of x that will maximize the volume. So we're maximizing the volume, and we want to figure out what is the maximum volume. So this would be a case when I'm looking at my volume equation that I have, and if I were to quickly understand, I'll write this over again just in case. Volume is x times 40 minus 2x times 20 minus 2x. You'll notice if you're trying to understand the degree and behavior of this polynomial that you've created, you don't have to because you can type it into your TI, but I'd like to explain a little further for you. Remember, if you have a degree, or if you're looking for, I'll say it this way, if you're trying to understand the leading term of a product of factors, you can basically take the leading term in each of the factors. So you can say x times negative 2x times negative 2x. So see, I'm just taking the leading term, the terms with the highest degrees. And then when you actually multiply them out, you end up seeing that you end up having positive 4x cubed. Well, the degree is 3. So it's a polynomial, and it's a little harder to find a maximum of a polynomial if you don't have a picture of the graph. If this was a nice quadratic function like we had earlier, we have different techniques where we can do this analytically. But because I know I have a degree 3 polynomial, I'm going to now we're going to use the TI to help us solve this. So what we'll have to do, we'll go back and we'll enter our volume in to interpret the graphs. So we'll switch over to our TI view, and I'll erase out what I previously have. And my volume formula, I believe I have x times 40 minus 2x times 20 minus 2x. And you don't have to multiply it up. The calculator will take care of this interpretation for you. You could use the previous window. So I'll just show you, maybe I have my previous window up and ready to go. And you can kind of see like, no, not really. Didn't really help me. So a lot of times if you're interested, you can kind of zoom fit it to get you a better clue of what the behavior is happening. You can also use some techniques from previous section to figure out the true sketch of a polynomial. You can kind of see, all right, let's look at our window now. It's like that y min's pretty small, y max. Maybe I'll change my y max. I could make it 24,000 as well. Let's see what happens. Graph it. So we kind of see that we have some sort of max happening. You don't have to do this, but I just want to show you what the purpose of the polynomial is doing. If I were to switch the x max to, like, let's say 50, just so that you can kind of interpret what's going on, you can kind of see the volume is a polynomial of degree 3, or odd at least, because the endpoint behavior is like down then up. But remember, we're looking for maximum volume, and the issue is you don't have to see the full range. You could actually kind of see and say, well, maximum volume looks like a local max would be somewhere over here. You can't see when I say over here, but I think you're guessing the right area. So we could actually use our calculator to calculate that. So we can do second trace, and the maximum, we'll press that's item number 4. And just move your cursor over to where you want to be. So left bound, I go a little to the left of my max, or what I think my max is. Right bound, a little to the right, and I exaggerate because it looks like kind of flatter. So, and what I have for myself, I have a maximum. The x value is 4.23 or so, and then the y value is 1,539.6 or so. So just kind of, so you're interpreting this, I could kind of show you. I'll copy this over so I don't forget. And we'll go back. If you don't have the copy and paste function, all you do is sketch your graph relatively quick. So we'll copy over. Probably have to copy on the side here. Try this again. There we go. And so you can kind of see at this moment, we found our maximum. So remember, you're answering a few questions here. The value of x that maximizes the volume of the box. Okay, so if we're going to answer that, that is the x value. X equals 4.23. Are we in inches or are we in feet or centimeters? Let's double check. Inches, okay. Units can be important too, so we have to be careful. 4.23 inches maximizes the volume. And then the maximum volume happens to be the y value. So that is 1,539 point, I'll say 6. And remember, volume has cubic inches, so you can say cubic inches. And the is should look like an is, not a 15. There we go. I try. So be careful what the problem is asking you. Sometimes it asks you for both X value and Y value, and sometimes it asks you just for the maximum volume. So just be careful and answer the right question. But you can kind of see that the TI is very useful in helping us determine this. So one last question. We want to understand, for what values of X will the volume be greater than 800 cubic inches? So this would be a case where we're still dealing with the volume. So the Y1 will be the volume, X times 40 minus 2X times 20 minus 2X. But we would need to understand comparison. So we're going to look at Y2 as 800, just so that we can kind of see where does the graph end up being greater than or above that line. So let's go back real quick to our TI, analyze just a little bit further, and we're almost there. So I'll use our new window, just with Y equals. We're looking at 800. And notice if I use my current window, I'm kind of looking at my graph and I'm seeing, well, it looks a little squished. I see two places where the volume can be above 800. There's two regions where the blue curve is above the red curve. Now, what could help you further is using the restriction. We can kind of tell already that we're going to delete out one of these possibilities. Let's go back to the window. Remember, our restriction was going from X is going from 0 to 10 inches. So the X min can be restated as 0, and the X max can be restated as 10. I graph it again, and it narrows down my options. But now you see my previous window is not so nice for me to determine. Everything kind of looks the same. So this is where I might play a little bit with my Y min and Y max. I feel like they're too big, so it's making the curve look a little bit too flat. So let's kind of keep this, maybe I'll start with going to negative 10,000. I mean, I might be too high either way, but negative 10,000. To positive 10,000, sometimes that just kind of gives us some symmetry and helps us see our graph. See how you see it's a little bit more curved. And you can definitely take it a little further. But remember, the idea is us finding these intersection points. So, if we want to, we can. We'll try to make it a little prettier for you. You deserve that. Let's just kind of cut it in half one more time. See, it's a little easier to drop it down than it is to keep building up. So graph this one more time. And now I'm seeing kind of a nicer idea of, oh, that is the region where the blue line is above the red line. Or I should say curve. So again, I'm going to copy this so I can kind of analyze it. And of course, you can do a quick sketch if you need to. And we're going to go back to our problem at hand. And I'll copy it on the right side. Now feel free. We can also hand sketch it if we need to help us show our work. So remember, I'll shrink it down just a little bit. For what values of X will the volume be greater than 800 cubic inches? If you're trying to interpret this, you're actually looking for this values of X that give you this region. So what that means, you would have to find the intersection of these two curves so that you can find this corresponding X value. I'll say X1 and X2. Because that region, everyone in between those two numbers, will give you where the volume is greater than 800 cubic inches. So if you'd like to, just like I said, you don't have to copy and paste graphs. You could just have a quick sketch of your window. You kind of see maximum volume, you see something happening here, and then again, you can say, oh yeah, I need to figure out what is this one and what is this X value. So remember, our region that we need would be including all those values in between. So this is again where we would take our TI. It's a little harder to solve this polynomial equation analytically, so we're going to utilize, we already have a graph. Let's go back one more time. and calculate this together. What's our favorite button? Second, trace. Yep. And we're going to calculate, this time it's our intersections. So I'm going to move it closer. To the first intersection, because sometimes the calculator chooses which one it wants to go. So first curve in the blue line, or curve, second curve on the red line. Make it guess. And we have our intersection to be 1 point, let's say 2, 1. And then the other one, second trace one more time. We're going to find another intersection. You can move your cursor over or your X value. I just want to be a little closer to the other intersection point because otherwise the calculator keeps surfacing or focusing on what you already calculated. So we shall do that. Make it guess. And we do have the second intersection point. That's at 7 point, let's say 9, 1. So we go back one last time, update our ideas, and say, remember what we just found. I now can erase my question marks because I no longer have questions. I have 1.21 and 7.91. So if I'm asking what values of X will the volume be greater than 800 cubic inches, you could answer it like so. We have 1.21 is less than X is less than 7.91, because that is including everyone in between those two X values. Or if you prefer interval notation, you could also say 1.21 comma 7.91, and you have your answer to part D. So now you guys will be experts with a little more practice with this cardboard box problem. And I will see you next section.